Hello, everybody. Hopefully you guys can hear me okay. Just want to welcome you to our whiteboard session. My name's Leah. I'm the marketing manager here at RGL, and I just want to give you an introduction to today's event. We're going to be exploring flow control device completions and how to mitigate the associated challenges. Today's open discussion is going to be presented by our in-house completions expert, Alberto Uzcátegui. And before we begin, I just want to go over a few housekeeping notes. We've noticed that the video quality of the presentation can be affected when our audience members have their video feeds turned on. So we're just asking that during the presentation portion of the open discussion, keep your video feeds off, and then towards the end of the session, if you have a question, then of course, feel free to unmute, turn on your video feed, and you can comment and interact that way. Just want to give you some background about our whiteboard sessions. It's one of the ways that we wanted to continue the active collaboration within our industry during this new normal. So at the RGL offices, our whiteboard sessions are where some of our best brainstorming, problem solving, and ideas could take place. So we wanted to carry that over to the virtual domain, and so here we are. Today's talk should take about 20-25 minutes, and afterward we'd love to turn it over to the audience to ask questions, interact, and of course we wanted this to be a bit of an open discussion format, so we'd love to get your feedback on today's viewpoints as well. Feel free to comment if you have a question during the presentation. You can add it into the chat window, and we can address it towards the end. And so to begin, I'd like to formally introduce Alberto. He's RGL's in-house completions expert. As a mechanical engineer, he has over 12 years of experience in oil and gas industry, working for both operators and service companies. Now, his focus has primarily been on drilling and completions design and operations for various oil production assets. Right now at RGL, his duties involve managing all business development and technical related activities for the Latin American region and providing worldwide completions engineering support. So let's get started, and Alberto, I'll let you take it from here.
Thanks, Leah, and thanks everyone for joining. Well, as Leah mentioned, today's talk is going to be about FCD completions and how we basically how FCD completions, they've been they've been for a long time around in the industry, right? So and they've been successful if they're designed properly. However, the main topic of today is not to discuss about the benefits of these technologies. It's more about how understanding these challenges and addressing them ahead of the deployment of this type of completions can definitely have a positive impact on the performance of this technology, and how minor changes could impact basically what could happen in the life of the well. So I've been referenced a lot of papers along the presentation, so feel free to write down these paper numbers of SPE and OTC, and some of them they're related to successful applications, so I'm not going to give any actual case study, but we are definitely going to talk about how to do and how to mitigate these associated challenges that these technologies bring with them. So let's jump into the presentation. So operators' concerns in terms of production and injection wells when they're thinking about utilizing these kind of completions are basically the reservoir heterogeneities and geological variabilities along the paid or the production section for the wells. So definitely you want to have these reservoir heterogeneities may have an impact on how the well is produced and how the reservoir is produced. And this could bring some challenges in how we definitely drain the reservoir. So one of them is the hill-to-toe effect, well known in horizontal wells. So let's say we have in this picture you see in your right-hand side, you have a uniform permeability, which is not true, of course, along the lateral section. And you know that you're not going to drain efficiently if you just have a liner along this length, right? So you're going to drain more your formation close to the heel, and probably not drained your formation effectively at the toe, or in some cases long laterals. You can be end by no draining at all your length, your total length of the well. So you're actually losing some money, you're leaving some reserves downhole. And for some consolidated formations like carbonates, that they do not collapse over the liner, we might, in some cases, you might be expecting some anodal flow. And this is, of course, not productive. You want to have as much radial flow as possible. So this is something you also want to mitigate and address. So why to consider FCD completions or reservoir optimized completions, and that depends on the type of applications you are in, right? So definitely for producers, you want to either block or delay your unwanted fluid. So in an oil well, you want to, of course, delay your water, gas, or stream breakthrough. This is, of course, going to harm your economics, and it can bring some catastrophic consequences to the well integrity. And of course, one thing that operators need to balance when they're doing economic analysis is not only the consequences of producing more of a fluid that you're not going to benefit from, but also all the costs that all the impact in economics that this brings, as we'll have to produce and use energy to produce that fluids to the surface, and then how to treat them, manage them, and then re-inject them in some cases. That is a big impact in terms of economics. And for injector wells, when we're talking about either secondary or tertiary kind of recovery mechanism, you want to definitely avoid fingering or short-quitting or bypassing these fluids that you're injecting, because you want to have a good sweep efficiency of either water, polymer, or steam flood, and you don't want this fluid to come straight to your producer well, because you know that, again, there's going to harm your well, or there's going to be problems with the efficiency of your EOR recovery that you're using. One of the well-known problems in the industry is hotspots. So these FCDs, they can definitely help with that, targeting, minimizing the flow velocity, the linear flow velocity. And what is important here as well is that not only FCDs, they play a big role, but also understanding how you complete your well. And for example, for unconsolidated formations, the sand control as well, that also have a considerable impact in minimizing that flow velocity per foot. So that's why operators, they use gravel packing or certain type of devices to kind of avoid these hotspots that, of course, again, they can bring some catastrophic consequences to the well. And as mentioned before, we want to minimize anodal flow in consolidated formations. We want to increase and enhance this rate of flow into the production tube, and so we drain the reservoir in a uniform manner. And at the end of the day, what operators and service companies we want is to maximize the oil recovery. Now, kind of to talk about FCD's applications. Let me just go back one. Sorry. To talk about the kind of FCD's applications. So we have either tube and deploy or liner deploy. So liner deploy, these completions are run directly facing the reservoir. So you don't have any casing between the tool or the FCD tools and the reservoir, and most likely you run that completions when you have a high level of understanding of your reservoir. So your degree of uncertainty is not high. And depending on the formation type, again, if you're in an unconsolidated formation, these tools are going to require some sand control. And while if you're in a carbonate formation, they might not need sand control at all, or probably a debris control, but nothing really with a high level of design. And when we move forward to tube and deploy completions, they're vastly used in injector wells, although for some repairs, you could also see some tube and deploy applications. And one of the main differences is that usually tube and deploys, is they're inside the casing, they do require some sonal isolation, like either friction packers, soluble packers. And it's important to design thinking in these kind of compartments, because again, in this case, you don't have information that is going to collapse, and then you will have reservoir will be more prone to anodal flow, right? So that's why you want to mitigate that with sonal isolation. And if you're in the case that a well failed due to the sand control fail, then probably these tube and deploy FCDs might probably consider some sand control. And the biggest difference is that for tube and deploy FCDs, usually you can consider them tube and retrievable. Sometimes it could be a challenge if you have a kind of like a type of sonal isolation packer, but still you can retrieve them. However, of course, they're more expensive when you talk about compare with liner deploy. However, you need to have a good understanding of how your reservoir performs to, be confident and run a tube and liner deploy completion. Now, so kind of talking about FCD types, so industry call them ICDs, AICDs. However, I wanted to group them in two because they can be used for injector and producers, and ICDs is only for inflow. So you can find passive FCDs, so they don't have moving parts, and even a single hole in a base pipe, that'd be an FCD because it could generate a choke and generate a pressure drop. And I've referenced again several papers there. Depending on the fluid conditions and the need that operators have, service companies design the geometries to be either a fixed choke or to react to the kind of fluid that is going through the tool, right? To react to the fluid properties like densities and or viscosities. And then you have some FCDs with moving parts, like the one you see below. The first two actually they're autonomous. So it's a valve, a disc that can that actually reacts to the properties inside. So the fluid properties are going to have an impact on how this opener closes, depending on, again, viscosity, density. And in more complex applications, you have ICVs, which stands for inflow control valve, which are commonly seen in offshore wells, where you have actually a hydraulic or electric line controlling a choke to be able to be, let's call, more in a smart completions well, and react to, usually these technologies come coupled with some sensors, so they react to how the properties of the fluids and sometimes even the amount of fluids, and they can choke even more or less depending on the conditions, and to have a better optimization of the well. Now, how do we design, and what's the FCD strategies that operators and service company must follow? And of course, that's why service companies requires a lot of information. It's critical to know as much as possible all reservoir parameters, and more importantly, all operating strategies that operators are planning in these wells along the expected well life. Economic consideration is a critical point, and it's probably some reservoirs, they could have some technologies could have a big impact, but probably they're not going to be economic feasible. So it's important to consider that. And in some cases, as well, as I mentioned before, operators need to understand that it's not only related to the cost of or the investment for these tools, but rather including the whole picture and how to handle, treat, and manage and re-inject that fluids that they don't want to produce in some cases, right? And how could happen if you don't consider these technologies along the well life. But the critical thing is that these technologies, you should consider them permanent, or you should design them for the expected well life. And that's why it's critical to address and understand all these risks ahead. So because minimum impact and minimum changes have drastic effects on how these technologies perform. So I bring here a pretty simple example. This is a Venturi nozzle, which is basically described by this equation. Is a mass flow, which is equals to the discharge coefficient, which describe all pressure drops along the geometry. So it's a geometrical constant of this kind of device. Then you have the area of this throat or of this choking segment, A2, and you have the delta P and your density. So if, let's say, you have a mass flow rate of 125 barrels a day, and the diameter, as you can see, is they're pretty small, is 4 millimeters or 10/64 of an inch, and the discharge coefficient is 0.45, right? So the delta P that you would need to produce that amount of fluid would be 117 psi. So now let's think what could happen, or let's see what could happen if you have some problems with either scaling or erosion, right? So with the minimum scaling, we decrease that diameter to 3 millimeters, so just 0.5 in thickness in reduction for the diameter, the pressure drop would skyrocket, right? So we would go over even more than 3 times to 371 psi. And if you're inducing scaling and you're increasing the pressure drop, this is a perfect recipe for keeping generating more and more scaling, and at the end you will end plugging your well or plugging your technology. And on the other hand, and in contrast, if you have erosion and you increase that diameter about 5 millimeters, so just one millimeter to 5 millimeters, the pressure drop would come down to less than half. So basically you would end not choking as you would expecting for that flow rate you design. And at the end of the day, you would definitely probably all the pressure drop that you would require to do the choking you were expecting, you would end not doing well as you would design before. And this would apply not only for fixed chokes like this one, but for also moving parts. It's even more critical when you have some moving parts. Having a risk of scaling or erosion would definitely lead to a malfunction of these technologies. So that's why it's critical to address that ahead. So now in terms of challenges and risk, main challenge is how do we design that? So as mentioned before, understanding is critical, all the parameters and all the operating conditions. And one of the things that I used to mention, because it's been seen in the industry, several problems with that, is to account for all expected pressure drop and to understand all pressure drops properly. Because when we were designing that, operators come with a drawdown, right, from your reservoir to your wellbore. But in some cases, in unconsolidated formations, for example, you have a formation sand that is going to collapse and is going to form on top of your sand control, and this is going to generate a pressure drop. So depending on the sand control you pick, the pressure drop is going to behave of one way or another one. So understanding that pressure drop would lead to, if you misdesign, you probably would end choking everything in your sand phase, and your device would end not doing anything or not choking it properly. And then you would end probably not choking as you designed for and producing all this unwanted fluid or not draining as you were expecting. And then analytical and numerical modeling it's critical, of course. Analytical modeling is very important because it allows operators and service companies to look into a detailed way and to solve complex physics and problems that you can find at a really detailed way. While when you're looking at numerical modeling, the reservoir simulation, of course, operators, they want to understand how the well is going to perform on time. And again, try to couple that analytical and numerical modeling is critical to have a good understanding of how the technology is going to perform over time. Mechanical integrity, that's well known for any completion tool. So you need to understand your installation loads. So target track is critical. And an FEA analysis for the tools is critical. And the reason why it's critical is because these tools, even if they're in a base pipe, of course, like a sand control screen or liner, they have small parts that they're all put together either by threading, welding, brazing, or any other manufacturing process. And it's critical to understand how all the loads that the tool or the completion is going to go through when you're running it and when it's working, how this is going to react, and if it's not going to have an impact on how the tools are inside that to have a good pressure sealing or keep performing as expecting. So it's critical to take into consideration that. Thermal loads, of course, in the SACD war or in the thermal war is extremely important, as you might expect some temperature swings and some fatigue as well. It's critical to design for high temperature as well. So that consideration should be made all the time. And in any case, when there's a challenging application, it is always recommended to go for full-scale integrity testing when you can apply some combined loading, like, for example, some bend-in, which would account for dot-like severity or tortuosity along a lateral, and then your compression and torque values that you're expecting. Some laterals, you can see some laterals of more than 10,000 feet and operators rotating over 15,000 pounds. So sometimes it's critical to consider that for these kind of applications. Erosion is a well-known risk, and how to address erosion is basically with the material selection. And sometimes when it's possible to kind of like have a geometry that is less prone to erosion. That's why, and when operators, they have a high uncertainty in terms of how the erosion would impact that tools, it's critical to do some analytical and CFD modeling. There are a lot of standards and a lot of equations for analytical. However, it's a complex phenomena because you're depending on what you have and how many sand particles you have and the impact angle that they're going to have. That's critical to replicate. So that's why it's if you have a high risk or high uncertainty, it's recommended to go to CFD modeling. I reference a pretty nice paper posted by CFER, I think it was last year in Canada, where you can actually do better or have a better understanding on how the erosion may impact an FCD. And if again the risk is too high, as seen below in these both case studies, it's definitely recommended to conduct some experimental testing which replicates or try to replicate the expected surface life. So you put a lot of particles and fluid at high velocity to see how the material in your technology is going to perform, and you avoid these critical issues that at the end is just going to harm and jeopardize the production, and even you can end losing your well and having to do pretty expensive workovers. Now, scaling is another well-known issue that affects a lot in this industry, and having a good chemistry understanding and understanding how the chemical interaction happens downhole with different kind of fluids that you're injecting, pH, salinities, different conditions, how they react under temperatures, if the temperature drops or increases, same for the pressure drop. It's pretty critical. So you come down to, you could look into material selection, that is important. And of course that when you come to material selection, you can do some testing where you can actually submit some material to a solution which may be representative of the formation. But what's critical is that scaling is a dynamic process, so it's extremely difficult to account for how scaling, how fast scaling is going to happen. So, and moving toward more dynamic testing is expensive. So, but again, if the risk is there, it's definitely recommended to look into that direction. And then in some critical applications, like for example, I've seen that in the pre-salt in Brazil, offshore wells, where they cannot afford to do a workover because it's extremely expensive. I've seen that some operators and service companies, they consider chemical injection mandrels upstream or below the valve that they use because they want to definitely try to reduce or mitigate that risk as much as possible. As it is well known, is a valve just get a bit of a scale and is going to stop performing as expected, and it's a pretty expensive technology in a pretty expensive environment. So that's why you don't want to end having, as shown in these pictures below, having partial plug-in, full plug-in. It's critical to understand scaling and address it, because in this kind of geometries, which are pretty small in terms of size, scaling is just going to probably kill your well pretty fast if you induce a fast way of scaling. And then to finish up in kind of like the challenges and risk, some of these technologies, mostly in injector wells, they might consider some sliding sleeve. And if you've been in this kind of applications, when you have a sliding sleeve that's been sitting or it's been running a well for several years, it's pretty challenging to go and shift it. However, you design that well because at some point of your well, you might need that sliding sleeve to be open or closed. So we actually brought this case study where we submit this, or we put that to sliding sleeve in actually in a tool to actual conditions, reservoir conditions for several weeks, and then different kind of treatments of the steel. And then we took them out and see how the corrosion and scaling builds up, and there was a big difference. And also when we did that shifting force testing, we found that in the case of the most corrode one, the force to shift that skyrocket. So you found also, as you can see in the pictures, some scaling build up, some corrosion build up, and it's critical to understand how this is going to create and form, because you design your well for that. So again, scaling corrosion understanding is critical. Having the proper shifting tool is of course mandatory, and sometimes enough hammering power, because it's gonna, you will need some 10 or 20,000 pounds of force to shift that sleeve. And what's critical in horizontal wells, it's to have a good centralization. If you don't have good centralization, you might not be ending having a good engagement of your tool with your sliding sleeve, and probably even if you try several times, you're not going to be successful shifting that sleeves. So to summarize and wrap up, I just want to say that the critical thing is that operators and service companies, they need to work closely and share information. And not only, that's why, service companies, we do require a lot of information, but not only service companies require information, but sharing information as well with operators is key to have that interaction and to mitigate all these challenges. And this would just allow operators to make, I would say, most informed decisions in terms of selecting one technology versus the other one, smart completions, ICD completions, AICDs, and also understanding, these challenges ahead to, again, make more informed evaluation or risk versus reward. So it's critical to have that understanding to be able to finalize with a successful application. And with that, Leah, I finalize and I put it back to you.
Great. Thanks, Alberto, for that amazing insight. I would like to open up the floor to our guests. If you have any questions for Alberto, please feel free to turn on your mic, turn on your video to interact in this open discussion. Alternatively, you can chat your question in the window in the message conversation. That's another option as well. So in the meantime, I do have a question for you, Alberto, of my own. I'm just wondering, is there a preference between tubing and liner deployed in order to avoid the higher risks?
Well, that's interesting. So liner deploy, tubing deploy. So it definitely comes down to, if you have the flexibility to go with a liner deploy versus a tubing deploy. If you have a failure in a producer well, you definitely want to go with a tube and deploy, right? But to reduce risks, if you have a good understanding of your reservoir, it's definitely recommended to go with a liner deploy. It's just going to save some money, right? While if you have not a good understanding and you've seen some failures, it's definitely would allow you to have more flexibility to go with a tube and deploy first. And see how this performs, and then later on you can just probably drill some new wells with the liner deploy completion.
Ya acabó la presentación, están haciendo preguntas y yo hice una.
There's a question in the text here.
Perfect. So Julian's wondering if you can expand on the sliding sleeve shifting scenario that we ran at the facility, and how did we simulate the downhole chemistry?
Yeah, absolutely. So that was run in a rig that was actually simulated in downhole conditions for a while. It was for a steam injection application. It lasts several weeks. And basically it was to actually understand not only how the corrosion and scaling was going to build up, as well as how the technology, the FCD technology, was going to perform. So we exposed that to several weeks of steam injection at the same temperature, same water cut, or same steam quality. So you have some water there to induce kind of like the conditions or the corrosion that you might expect. And after these several weeks of injection, then we took them out, and then we actually complete a shifting testing. So you go with your same. We of course in any tool we have to do testing prior. We ship the sliding or the tools with sliding sleeve to the field, and we have that values of course calculated and well understood. And then when we took them to our facility and did that testing, we did exactly the same shifting procedure, engaged the shifting tool, and then we measured the force we need to apply to effectively shifting that sliding sleeve under these control conditions. And we saw that, the shifting that sliding sleeve, the values, went from let's say 1 to, in some cases, 2.53. So that's what is, and in the field, if you look at how much force you need, sometimes you could be talking about 20,000 pounds of force to be able to shift that sliding sleeve in producer wells where you're actually more prone to have some sort of like emulsion or asphaltene or scale build-up deposition.
Okay, great question. So we have another question. This one's from Walter. What's the maximum viscosity value that these tools could be used? This is Walter from Venezuela.
Yeah, that's a lot. That's a common question, and that depends on the technology, of course. So, and it's critical, right? So I've seen applications up to 2,000 centipoise. After that, if you're thinking about it's driven not only by viscosity, but as well the fluid velocity. So if you have creep flow and you know when you're producing, you have really the fluid that is going through that technology is pretty slow. So having a high viscosity could make things really complex. So proven in the field in terms of the whole that's kind of universe of these applications I've seen. We would be talking about 1 to 2,000 centipoise. I've never seen something higher than that. And the reason is that, and it's pretty complex to test because then you have to have some special pumps that can pump that really high viscous fluid. So it's pretty complex to conduct, right? We've tried to do some analysis for crazy viscosities over 10,000 centipoise, and I can tell you it didn't work out. So that's what I can say. That I don't have the limit, but I can tell you, and we did some analysis and CFD calculations, and 10,000 or over 10,000 centipoise, it doesn't work out. So what I've been seeing in the industry in some successful experiences is 1 to 2,000 centipoise.
Okay, great questions. Well, we've actually hit our 2 o'clock mark, so we will have to cut it there, but I just want to wrap up and thank everyone for watching today. If you find that any of this chat is interesting, you can share it to your colleagues. We're going to be posting it later this week on our YouTube channel for permanent viewing, and you can find us on YouTube by just searching RGL Reservoir Management, or you can check it out on our LinkedIn company page as well. So stay tuned for updates on our next whiteboard session in the coming weeks. If you need any more information, you can always visit our website at rglinc.com. And again, Alberto, I'll thank you for giving us such expert insight. And thank you again, everyone. Enjoy the rest of your day. Take care.
Thanks, everyone.
Thank you, Alberto.
Thank you for joining. Thanks.
Thank you, Leah.
Thanks, Alberto.
Thanks, Alberto.